Deep beneath your feet lies a sophisticated industrial empire that has been running flawlessly since the age of the dinosaurs. These aren't just ants. They are master engineers running complex fungal monocultures in climate-regulated bunkers, complete with ventilation shafts, sanitation corridors, and waste-to-resource circular systems. 50 million years ago, they invented controlled environment agriculture. Today, we are deconstructing their hidden laboratories to reveal the ancient blueprint for survival that we're only just beginning to understand. Hi, welcome to Wild Spaces. If you care about food security, sustainable farming, or the next wave of green tech, this video is for you. We are tearing open subterranean ant labs to pull out practical tactics that modern agriculture, from vertical farms to family plots, are already copying. By the end, you'll see how our cutting-edge inventions are often pale reflections of solutions evolved long before humans walked the planet. Start with scale. Leafcutter ants, genera Atta and Acromyrmex, cultivate a single fungal species inside huge subterranean gardens. Colonies can contain millions of workers and hectares of fungal substrate. They don't farm plants directly. They farm fungus using freshly cut leaf material as feedstock. Their gardens are true monocultures, one cultivated fungal species per nest, protected by worker policing and antimicrobial chemistry. Ant nests are not passive holes. They are climate engineered. Workers excavate interconnected chambers and vertical shafts to regulate airflow, humidity, and temperature across fungal gardens. Researchers found microventilation shafts and structural designs that maintain stable humidity and prevent fungal spoilage. Think of these as natural HVAC systems, passive, low-energy solutions. That exact functionality is what modern vertical farms need to optimize energy use and crop health. Leafcutters manage waste like a closed-loop system. Old or contaminated fungal combs are removed to refuse chambers. Waste is segregated and partially composted, limiting disease spread. Workers sort, quarantine, and recycle, converting plant waste and dead ants back into microbial resources. This is biological waste management at scale. A social, insect-built bioreactor that prevents pathogen outbreaks and recaptures nutrients. Ant colonies solve complex problems with simple agents following local rules. Swarm intelligence. They allocate labor dynamically: foragers, gardeners, waste handlers, defenders. The result is resilient, scalable agriculture without centralized control. Modern robotics and agritech are adopting this model. Hundreds of simple robots coordinate to plant, monitor, and harvest, avoiding the single-point failures of big machines. In 2026, we're finally seeing vertical farms, soil startups, and cooperatives adopt ant-inspired solutions. Here's a breakdown. Thermal regulation in vertical farms. Companies using passive ventilation and microclimate zoning modeled on ant shafts. Examples: InFarm, Gotham Greens using zoned climate control. Soil sensors and water reduction. Farmers using distributed, low-cost sensor arrays and decision rules inspired by ant brood and fungus sensing to cut water use by approximately 40% in arid regions. Composting and value-added organic inputs. Small producers adopting ant-modeled layer composting, segregated inoculated piles, to rapidly turn horticultural waste into premium soil amendments. Biological pest management. Local cooperatives using microbial and insect-based pest control routines modeled on ants' antibiotic-producing actinomycete symbionts to reduce chemical inputs. Microbiome treatments for resilience. Products that condition plant microbiomes echo ant cultivation practices, promoting plant immune function and drought tolerance. Let's look at people using ant-inspired tech today. Case A. A cooperative in Spain using decentralized sensor networks and ant-style zoning to reduce water use by 40% in almond orchards. Case B. A Midwest regenerative farm using ant-modeled compost layering and microbial inoculants to convert 100% of harvest waste into soil amendments, reducing purchased fertilizer by 60%. Case C. Vertical farm startup implementing passive ventilation chambers inspired by nest shaft geometry, lowering HVAC energy use by 20% in pilot trials. These case studies combine published research with documented pilot projects from startups and agri-extension programs. Practical checklist for small farms and gardeners. 1. Passive microclimate zoning. Partition greenhouses into smaller chambers with controlled air paths. Add low-energy vents inspired by ant shafts. 2. Segregated compost/refuse areas. Remove contaminated plant material to a separate inoculated pile to speed decomposition and prevent disease cycles. 3. Sensor swarms. Deploy many cheap sensors, soil moisture, temperature, CO2, and use rule-based automation rather than a single expensive controller. 4. Microbial inoculants and biocontrol. Trial locally adapted microbial mixes that strengthen plant-associated microbiomes. Use biologicals before chemicals. 5. Cooperative resource sharing. Mimic ant division of labor. Form local shares for specialized tasks, robot maintenance, microbial culturing, composting hubs. The humbling reality. Ants engineered sustainable, low-input, resilient agriculture 50 million years ago. Modern tech isn't inventing these ideas, it's rediscovering them and translating them into human-scale tools. If we want sustainable food systems that last, looking down, literally into the soil, might be the smartest place to look. If you found this fascinating, hit subscribe and ring the bell. We break down ancient innovations that solve today's problems every week. Like the video to help it reach farmers and innovators. Comment, which ant-inspired idea would you try on your farm or garden first? I'll pin the best answer.